Hey everybody, Mr. Judson here. So today we're starting to look at trying to gain more information about polynomials. Remember, a polynomial is something that's written like f of x equals x cubed plus 4x squared minus 2x. It's that type of equation. And the exponents really can get as big as we want them to. I mean, I don't want to see anything like x to the 20th. I don't want to see that. But whether it's x cubed or x to the 4th or x to the 5th, I want to be able to know some things about what that graph looks like without even really having to do much work. Okay? So one of the things we want to talk about is this thing called end behavior. And what it refers to is, what does my graph look like way out on this end? Or what does it look like way out on this end? Okay? So what does the graph look like out on the ends? So here's an example. Let's say we have something like f of x equals 3x to the 4th minus 2x squared plus 7x minus 5. If I had to graph this, what does it look like out on the ends of the graph? Well, if I go out here and I take a positive number, let's say a large positive number, and I plug it back into this function, this is what we refer to as the dominant term, the highest exponent. It will dominate what this graph will do. So if I take a positive number and I stick it in here, and I do a positive number to the 4th power, that would be positive, times 3, that's positive. That means that graph will increase as we go out towards the right end of it, on the right side. Now if I go this way, if I take negative numbers and I raise it to the 4th power as well, a negative number times itself, 4 negative signs, that's a positive number, times 3, that's positive, and so this graph will also increase out to the left. So how do we describe the end behavior? We would say that f of x increases to the right and increases to the left. As I go out to the left, so if I start the origin and I go this way, these values are going to be increasing. And if I go off to the right, these values are increasing. Now, what's it going to do in between these two things? I don't know. That's another story. We have to work on that as well. But in terms of end behavior, I can kind of tell what these graphs look like out on the ends just by looking at that highest exponent and thinking what's a positive number raised to the 4th and what's a negative number raised to the 4th. And if this coefficient, now our book talks about the leading coefficient test. If that 3 was negative, what that's going to do is flip everything over, right? I would do a positive number times a negative, and that would make me go in the negative direction, and same thing over here. So then I would say that this function is decreasing to the right and decreasing also to the left. Okay? What about this one? I want you to describe the end behavior for this function. What's it going to look like? You guys go ahead and give it a shot. All right, so if I was going to graph this, I would think to myself, if I went way out this direction, I took a positive number, and I plug it in. This is the dominant term right here, okay? If I plug a positive number into here and I raise it to the 3rd power, I'm going to get a positive result. But then I'm going to multiply it by a negative 5, and that would be a negative result. So this function is going to decrease to the right. If I go this way, and I choose a negative number raised to the 3rd power is negative, that negative answer times a negative 5, that's positive, so this function is going to increase to the left. Okay? And if you want to, you can just pick a number. You know, pick a number like 8. If I stick the number 8 into here and I cube it, I don't know what 8 cubed is, but some big number, times negative 5, that's a negative number, so I'm going to get some negative y coordinate way down here somewhere. Or on this side, if I choose something like a negative 8, and I raise that to the third power, a negative times a negative times a negative, that's negative, times one more negative, that's positive. That means we're going up as we go to the left. So here's my end behavior. F of x is increasing to the left and decreasing to the right. And what we're going to do is we're going to develop some tools that help us graph this function. This is just one tool that helps us know what's going on way out at the ends. What's happening on the ends of this graph. Still got to figure out what's happening in the middle, and we'll get there, but this is going to help us determine what a graph would look like. Okay? All right, so something else that we want to use to help us out is something called turning points. How many turning points does a function have? Well, if I have something like this, f of x equals x squared plus 2x plus 1, okay? I know that what that looks like is a parabola. And there's one turning point. As I come along this, let's just say this was a road, as I come along, I'm going to make this one big turn, and so this would be considered a turning point. I was going down, but then I turned and went back up. Okay? What if I have something like f of x equals x cubed plus x plus 1? Well, we already know what a cubic function looks like. We graphed that in the chapter 1 with our basic functions. It looks something like this. Okay? Or a cubic function could look like this. It just depends on, you know, all the different terms and whether they're positive or negative and how big their coefficients are. But this curve, actually both of these has two turning points. Okay? So here's the first turning point right here. I'm driving along this road, I turn to the right, all of a sudden I stop, I straighten out my wheel, I'm going straight, but then I turn back to the left. So this would be the second turning point. Here, I'm driving along the road, I did a big hairpin turn, straightened out, and then turned again. So there's my first turning point, and there's my second turning point. Okay? We're not saying how far you turn as you go through this graph. But the number of turning points will always equal one less than the highest exponent. Okay, so here my exponent was 2. Subtract 1 from it, we get 1 turning point. Here my exponent's 3. You subtract 1 from that, you get 2. So there's my first turning point, there's a second. Got one here and here. You know, what if this was x to the 4th? Well, then there would be 3 turning points. Sort of. Don't you hate that? Sort of. If I have x to the 4th power plus, we'll just say whatever, dot, dot, dot. Okay? Sometimes an x to the 4th graph can look like this, which almost looks like a parabola, but it's a little more U-shaped to it. I don't see 3 turning points there. Okay? But an x to the 4th could also look like this. And then there's 1, 2, 3 turning points. Okay? So this is something that's designed to help us graph I hate saying this with math, we almost have to call it a sort of rule, right? Because, like I say, I don't see four, maybe you can make the argument there's 2 turning points there, but I don't know. So, we should say, at most, there is 1 less than the highest exponent. There will not be any more turning points than that. Okay? What else do we have to help us graph? Well, we know how to find x-intercepts, right? Set the function equal to 0 and solve. Or what if I had something like this? There's 1, 2, 3 x-intercepts. See, if I can find the number of x-intercepts, and I know something about end behavior, whether it goes up or down, whatever it does, and I also know a little bit about turning points, what it means is I could come pretty close to drawing an accurate graph by just finding those pieces of information. And that's really what we want to get to for today. How could I graph a polynomial using things like end behavior and turning points and finding the zeros? If I put all that together, can I get a picture that's close to what this thing should look like? One more thing we want to talk about. Multiplicity. This is the number of times that a 0 occurs. Number of times a 0 occurs. So for example, let's say I had f of x equals x plus 1 times x plus 1 times x minus 2 times x minus 2 times x minus 2. And let's say I asked you guys to graph this. That sounds like it might be kind of hard, but it's really not that hard. So x equals -1. So I know I'm going to have a 0 at x equals -1. But I know it's going to happen twice. So this has a multiplicity of 2. All right? And I also know there's going to be a 0 at x equals 2. Right? Whatever makes this equal 0. If I plug a 2 in here, here, or here, this has a multiplicity of 3. Now, why would that be important to me? Well, if the multiplicity is even, what that means is on the graph at -1, this graph does not go through the x-axis. It bounces, okay? If this is my x-axis, it goes like this or like this. Okay, now I'm not sure if it's above or below yet. I don't know. But something like this is going to happen. Okay? Either a low spot, a relative minimum, or a relative maximum has to hit that point. If your multiplicity is odd, this is really just about odd or even. Okay? Anytime the multiplicity is even, this is what happens. It bounces off the x-axis. If it's odd, then at 2, our graph has to go through the x-axis at that point. All right? Odd multiplicities always go through the x-axis. Even multiplicities bounce. That's actually it's a huge idea that can help us be pretty accurate with what a graph looks like. Okay? So let's graph a polynomial. All right, so I want to be able to graph this function, and what I'm going to do is I'm going to think about things like, what are the zeros, my x-intercepts? What's the end behavior look like? Is there a multiplicity that's even? Could that help me out? I want to look at all that information, okay? But the first thing I need to do is I need to set this thing equal to 0 and factor it. So what I'm going to do is I'm going to factor a -x out of each of those. The reason I'm taking a negative out is because of that leading coefficient that's negative here. All right? I don't want that. I want to start out with something positive in here. So this is going to be x squared. If I divide by a negative, that means this will be negative. Take an x out, I've got 2x. Divide this by a negative and take the x out. There's what I get. And then I want to factor this, so I've got a -x times, this would be x times x. Two numbers you multiply to get 8 and subtract to get negative 2. That sounds like a positive 2 and a negative 4. Right? And if that's equal to 0, that means my zeros are going to be at x equals 0, negative 2, and positive 4. Now, none of those happened twice. Each of these zeros happened exactly one time, which is an odd number. That means I have to go through the x-axis in those 3 spots. Okay? So if I'm going to graph this, I know that I'm hitting the x-axis at 0, at negative 2, and at 4. Now, at this point, does the graph look like this, or does it look like this? That's where our end behavior is going to help us out. Okay? So if I take a positive number and I plug it back in, into my dominant term. So a positive number raised to the 3rd power, that's positive, and then the negative of that is negative. That means I'm decreasing as I go to the right. If I take a negative number over here and I put that in here, remember you got to do the x cubed first. Don't look at that negative sign. You can do a negative number to the 3rd power, that's negative, and then the negative of that negative is positive. That means my end behavior this way has to be increasing because I got a positive result. Right? It's just like if I said, let's take a negative 5 and plug it in here, what I'm going to get at the end is a positive number, so I got to have a point up here somewhere. If I take a positive number and plug it in, even though there's stuff going on here, this is my dominant term. If I put a positive number in here, I'm going to get a negative result overall, and so there's going to be some point down here somewhere. I don't know where. I don't really care. I'm just trying to draw about what this graph looks like. And I think at this point I know. You know, I'm going to go down like this a little bit, come back up. It's going to do something like that. Now, is this a perfect graph? No. What we're going to do is we're going to call this a sketch. A sketch means we're getting close to what this graph looks like, but it's not perfect. You know, if I want to do a better job, I might need to plug in a number here to see how high this relative maximum should go. And one of the things we'll talk about is plot a sufficient number of points so that you know what it looks like. So if I made an XY table, and I really want to know exactly where that is, I should plug in a number 2 and see what I get. And if I look at this, you know, I always choose what's halfway in between. Okay, negative 1, I should plug in a negative 1 back into this whole function and see what I get. And then I can plot those XY coordinates and I have a better graph than what I have now. Me personally, I'm happy with that. When I ask you to draw a sketch, I want to know about what does this function look like when you graph it. All right? Let me give you guys one to try. All right, let's see if we can graph this function. So one thing we don't want to forget about, and it's a point that's always the easiest point to find on a graph, is the y-intercept. Let's not ever forget about that, okay? The y-intercept means if I plug a 0 in for x, I'm going to get 0, 0, negative 40. There's my y-intercept. Always an easy point to find. And you know, as long as we have to graph something, if we've got an easy piece of information, let's get it. Let's go ahead and get that. Okay, now I'm going to find the zeros. So I want to factor this. So first thing I'm going to do is I'm going to factor out a 2 just so that the numbers are a little bit easier to work with. All right, and then I'm going to do this. So let's see, that would be x squared times x squared. Two numbers you multiply to get 20 and subtract to get a negative 1. sounds like 4 and minus 5. So if I'm looking for zeros, this will never equal 0, right? 2 is 2. 2 cannot equal 0. If I look at this, right here, I will never be able to make that equal 0. Never. Why? Well, because if you plug, let's say you plug a negative number in, the moment you square it, you get something positive. You're going to add 4, you just have a bigger positive number. Plug in a positive number, square it, you get something positive. Add 4, you get a bigger positive number. That will never equal 0. So my only zeros will come from this. X squared minus 5. What would it take for that to equal 0? Well, move the 5 to the other side. And then take the square root of that. And x equals plus or minus the square root of 5. So I got 2 zeros, or x-intercepts. Even though we think there should be 4, 2 more of those zeros are going to be imaginary ones. And I know we haven't talked about imaginary zeros. What does that mean? Don't even worry about it yet. It just means we're only hitting the x-axis twice on here, okay? So let's see, the square root of 5 is about 2.24, okay? About 2 1/4. I don't have to be perfect. I just have to get it in about the right spot. So if I'm going to graph this, I'm going to hit the x-axis at plus or minus about 2 1/4. So right here and right about there. I also know that because I'm raising this to the 4th power, so now I'm thinking end behavior. What is this graph going to look like out on the ends? So if I take a positive number and put that to the 4th power, that's positive, times 2, it's still positive. That means I've got something like this going on. And if I take a negative number and plug it in and I raise that to the 4th power, that's positive, 4 negative numbers. Okay? Negative times a negative is positive. This negative times a negative is positive. That positive times this positive is positive. So we're going up this way as well. I also know my y-intercept is at negative 40. So if I count by tens, 10, 20, 30, 40, I know I've got to hit this point. So what does everything else look like in this graph? I don't know. It could do something like this. It could do something like this. It could do something like this. Or it could even do something like this. And I really don't know unless I do some more math. And now we're starting to get into calculus. In calculus, we learn how to decide what's going on with this thing. So for us, about the only thing we can do to see exactly what that looks like is to either plot additional points. I make an XY table and I just start plugging numbers in and see what happens. Or I need to take a look at a graphing calculator. Okay? So let's graph this real quick and just see exactly what's happening here. So let's see, I've got 2x raised to the 4th minus 2x squared minus 40. And before I graph it, I know, let's see, I'm going to go zoom option 4. And then I need to get down to negative 40. So let's take my window and let's change my y values. Let's go from like negative 50 to 10. And I'm going to count by tens. So it'll kind of match what we have here, sort of. There you go. That was one of the things that we said. Okay? So if I get back to this, my graph is going to look like this. So one of the questions that probably comes up right now is, how are we going to know, and what if this is a test question? I don't want to miss it. Well, I won't give you something like this where there's all those different possibilities. You know, I'll give you guys a problem where it's real clear what's happening, and you'll know for sure. All right? All right, let's try one more. All right, so here's a function that is already factored for us. It's kind of nice, helps out a little bit. And what we want to do is we want to draw a sketch of what we think this looks like. Find the zeros, think about the end behavior, think about turning points, multiplicity. What would this function look like? You guys try it. All right, so I mean, right away I know that my zeros are at x equals 2 and negative 3. It's already factored, so we can see that. This happened twice, so that means there's a multiplicity of 2 there, and so that's a point where my function's going to bounce off the x-axis at x equals 2. So if I graph this, if I start by plotting my zeros, I know there's one right here at negative 3, and there's one right here at 2, and my graph is either going to go like this or like this. I don't know yet if it's above or below. Okay, I'm going to need to check some more things out. So if I was to multiply this thing out, I don't really know what the answer would be, but I know it would be something like this. X cubed plus ... Right? When I square this, I'm going to square the first term, multiply the 2, and double it, so I'll get an x squared term. And then I'll take this x times that to produce that x cubed term. The only reason I really want to know that is so I can check my end behavior. Right? Because the only term that matters is the first one with the highest exponent. So if I take a negative number and cube it, I should get negative results. So that means this function is decreasing as you go to the left. Where over here, if I take a positive number and plug it in, a positive number cubed is positive, and so I'm increasing as I go to the right. 2 had a multiplicity that was even, so I know I'm going to bounce right here. Here I'm going through the axis. The other thing that I could check is, what's my y-intercept? If I plug a 0 into here, what do I get? Well, put a 0 here, you got negative 2 squared. That's 4 times 3. That's 12, so 0 comma 12, there's my y-intercept. So let's just say we're going to count by 2's. That's 2, 4, 6, 8, 10, 12. I got to hit this point. So here's what my graph looks like. Now, do I know that that's where the high point is? No. Matter of fact, the high point is probably halfway between these 2 points. So maybe it's a little bit to this side. So if I drew that again, maybe I would draw it more like this. And maybe this, if I clean it up, just so it looks like that goes straight through that point. I would say right there, that's a pretty good graph. Now again, if I'm not 100% sure and I want to be a little more accurate, well then I should plot a sufficient number of points so I feel confident. Maybe I want to take a negative 1 and plug it back into this function and see what I get for a y value. Put a negative 1 here, you've got negative 3 squared, that's 9. Put a negative 1 here, you got 2. 2 times 9, that's 18. I got to go higher. I need to go up even higher, right? But I would say this is a pretty good sketch. Remember, sketches don't have to be perfect. They just have to be close. All right, that's what we have for today. Let me get you guys a homework assignment. All right, so assignment number 10, we're in our 10th week now. We're doing page 148. We're going to do 1 to 8, all of those. We're going to do 9, just part D, 17 to 19, and 33 to 38. All right, that's all I got for you today. You guys stay safe. See you next time.